My name is Elena Savinson, and I am presenting our pictorial, A Walk in Nature, exploring the creative potentials of a generative design tool for soft robotic surfaces that foster a connection with nature. This work is co-authored by Dr. Keith Green of the Architectural Robotics Lab at Cornell University. We're developing soft robotic surfaces designed to support emotional well-being for inhabitants of urban environments who have limited access to nature. The robotic surfaces are capable of several behaviors used for therapeutic purposes, including guided breathing exercises, performing soothing movement inspired by the rhythm of ocean waves, as well as providing biofeedback by changing the inflation rate to tangibly visualize the biosignals of plants and human and promote a connection with plant life. Our earlier prototypes are pneumatic wall panels made from elastomer silicone with 9 air channels that are driven by numerically controlled pressure regulators. Our previous research has found that soft robots can cause experiences of discomfort or an uncanny valley-like effect due to the synthetic materiality and movement of the surfaces, which appears to be lifelike but not quite natural. Our goal in this study was to address these negative reactions. Thus, we decided to explore how participation in the design process and elements of biophilic design can be used to improve users' perceptions of our system and increase their natural sensibility. There are a few frameworks we used to inform our work. First, we looked at research on how to foster attachment to objects in our environment, which suggested that experiences of self-extension, where your identity is tied to a product, as well as positive memories associated with products, can increase one's sense of attachment. We utilize computer-aided design to create a generative design tool that enables users to upload a photograph that steers the design of a personalized soft robotic surface. We were also motivated by the biophilia hypothesis, which posits that humans have an evolutionary desire to affiliate with nature, and even further, that environments without natural elements might have negative effects to our mental well-being. Biophilic design is a strategy that operationalizes the biophilia hypothesis. There are 3 strategies of biophilic design. Provide direct experiences of nature through interactions with natural elements such as plant life, indirect experiences of nature such as images of nature or natural analogs, and experiences of space and place, which evoke an ecological attachment to a particular natural location. In this project, we included all 3 strategies. Our researcher questions were: 1. How can direct and indirect experiences of nature and associated memories increase the biophilic perceptions of an interactive system? And 2. How might participation in a CAD process through personalization increase a sense of attachment to the design outcomes? To study this, we conducted a concept validation experiment where 4 participants were asked to take a walk outdoors and take photographs of geometries found in nature using their smartphone. These images were uploaded into our generative design tool to make a personalized design for a soft robotic surface. This also allowed us to test the robustness of our tool by uploading a wide variety of imagery to determine if it was capable of handling photographic inputs with different qualities, such as color, brightness, and contrast. The images were geotagged and uploaded in a GIS software to make a map of each participant's walk outdoors. These maps were shown to the participants in a graphic package that was presented with their final design outcomes to help them remember their walks, increase positive memories and associations, and evoke a sense of space and place, the 3rd strategy of biophilic design. For each participant, 2 images were selected to create corresponding soft robots. This is an overview of our generative design tool, which was made in Rhinoceros 3D and Grasshopper, which includes image processing, edge tracing to make a curve, an interactive genetic algorithm, and a physics simulation to provide a realistic animation of the robotic surfaces. The image processing algorithm passes the bitmap through 3 filters, which removes unwanted details and identifies an edge curve that defines the outer shape of the surface. Once the edge is found, a 3D model is produced which is run through an interactive genetic algorithm, which operates in a manner akin to natural selection to create a set of designs that can be tuned by selecting parent designs that guide the appearance of future generations. Here is a sample of 4 designs created by the Generative Design tool that display variation in the edge profile and the grid of air chambers. In this set, number 1 and number 3 would be selected as parent designs because they are the most suitable for the fabrication of a working physical prototype due to the arrangement of grid cells, while also providing some aesthetic variation. Here is the total set of images and resulting design outcomes. These were compiled into the graphic packages and shown to the participants for feedback. From each set, 2 final designs were selected for a rendered simulation. The simulation included an overview of the design, as seen here, as well as demonstrating how the surface would appear during inflation. The simulations give an accurate representation of the physical prototypes. After the images were shown to the participants, we used an online questionnaire and follow-up interviews to gain feedback on the participants' experiences during their walk outdoors and how it affected perceptions of the design outcomes. We asked participants to select one robot design that they would choose to have in their home. They were presented with 3 options: the 2 designs from their photographs and a rendering of the initial rectangular prototype used in previous user testing for comparison. All 4 participants selected one of the generative robots. Comments that explained their selection suggested that participants preferred the organic shapes because they seemed more natural, but also because of the connection to their imagery, suggesting that some participants experienced a sense of self-extension. We also asked the participants to rate the designs using descriptors associated with biophilia. Designs that were rated higher for the descriptors natural, fascinating, mysterious, and complex were considered more biophilic. The pattern of the ratings showed that the generative designs were generally considered more biophilic. However, the feedback also suggested that some of the designs still created experiences of discomfort, as some of the less preferred generative surfaces were still described as unnerving. Other survey questions found that all the participants felt the maps helped them to remember their walk outdoors, and most participants felt a sense of ownership over the design outcomes, indicating experiences of self-extension. However, we also found that not all participants felt that the walk outdoors was sufficient to create a sense of attachment to the design outcomes. One participant stated that they felt the special meaning would develop over time based on their interactions with the robot, in the same way a person might develop a love for a certain coffee pot they use every morning. They did not feel the digital prototypes held special meaning because the photographs were of natural elements they merely happened to walk past and notice due to the study instructions. They believed the surfaces would foster a stronger sense of attachment if tied to a cherished memory, such as a flower they picked on a great vacation, a mountain in their hometown, or a tree behind their childhood house. The results therefore suggested that incorporating direct and indirect experiences of nature, memories, and a connection to space and place did seem to increase the biophilic sensibility of our system. However, we found that the use of participant photographs to generate designs did not always evoke emotional attachment. The study was very helpful for us to investigate how we should approach the design of our system, and we learned that it is more impactful to focus on designing systems that foster a deeper relationship with nature over time through the quality of the interaction. Informed by the feedback from our study, we made 2 physical prototypes to demonstrate that our tool can be used not only for simulation, but also to create files for digital fabrication. We started first with a small prototype, which had a live plant adhered to the surface. Once this was successful, we used our tool to create a larger prototype with 3 robotic surfaces connected by a frame. We sourced a large piece of wood for the frame to add another natural material, which was sculpted into shape using CNC milling. We also CNC milled molds that were used to cast the silicone surfaces in 2 parts and welded together using more silicone. The surfaces were attached to the wood with 3D printed trays with valves that allow for the air tubing to be plugged into the device. Live moss was adhered to the grid channels on the wooden frame to add even more plant life to the system. We tested the prototype in the lab and found that it was successful at performing the same inflation behaviors previously established with our rectangular prototype. We have begun user testing with our new biophilic prototype, and people have been responding well to the new design. Thank you for listening to our presentation. If you are interested in this project, we encourage you to read the full pictorial for more details.